Hi, everyone. It's a pretty hard spot to be after the wonderful talk we just had in front, but I'll do my best. I work for a company called Guavas. We are a startup headquartered in California, and we cater mostly to the telecommunication industry, and we build big data analytics applications to cover a range of needs for the communication industry. Mostly in service assurance and customer experience. So what I want to focus about today is more about the operational intelligence part of our activity, and more specifically what I call the anomaly detection. So what we do internally is that I'm responsible for a group that will actually build algorithms internally and then expose APIs to our internal developers. So it's a bit of a different setup from the talks we've seen previously, yesterday mostly, where you expose APIs on the web. Here I'm mostly talking about building predictive capabilities and then exposing that to our internal developers. So when we talk about operational intelligence, what I mean by that business word, if you want, is that you try to monitor a service. So it could be sensor data from a telco tower. It could be the quality of experience that your users have when they watch videos on your network, or it could be all sorts of things like that. And the first thing you want to do is monitor that data, obviously, and detect when something goes wrong. But detecting when something goes wrong, that's what we'll call anomaly detection later, is only the first step in the process. Obviously, it's already very valuable to know when something is going wrong for your customers, because any impact on your customers will obviously have a detrimental impact on your business as well. But what we do next is trying to really understand what is going wrong in the systems. You could have multiple alarms going on at the same time, but only one problem is really causing all those alarms. So the root cause analysis piece, which I will not be talking about today, is obviously critical as well to the analysis. And once you've isolated really what's going wrong, then you're pretty much halfway to solving the actual problem. So talking about anomaly detection, I found this definition of anomaly where it's something that is unusual or unexpected. What that means is that based on the history of what you've seen in the past, you just didn't expect what happened next. So in this case here, if all you've seen of your data, so this is time and this is a KPI that you're measuring, and if all you've seen is this much, then obviously you don't expect a spike going down at this point in time. And other cases could be when you have a step function like that, or other cases could also be when you have maybe a slow degradation of your system. An example here could be you have a memory leak in your application. So slowly but surely, you're running out of memory, and the application is swapping more and more, so it's slowing down. But it's fairly gradual, and it's probably even harder to detect. So that's the anomaly part. The detection part, what I mean by that is that you're trying to figure out when those events happen, but as I say here, without specific cooperation from the source. So you don't have any labels. You don't really know what really is or is not an anomaly. And this is really the unsupervised learning part if you talk in terms of machine learning. So no labels, so a lot of the APIs that we saw yesterday, for instance, could not be applied in this system. And it means that a lot of the times when you do anomaly detection, it's something you have to do more like in-house development, because there's a lot less standardized ways of doing it, and it depends a lot on your data. So in terms of implementation, if all you have is a signal like this, then you can, yes, maybe manually set a threshold above and a threshold below, and maybe that will solve your business problem, maybe not. But the problem with doing those rule-based and manual thresholds is that obviously it doesn't scale. We're talking here about monitoring millions of time series at the same time, for instance. So you need a much more automated way of doing that anomaly detection. So this is what I'll be talking about today, about how to automatically monitor all those time series in parallel using machine learning, but probably a different type of machine learning from what you've heard until this point. So I'll give you a brief example of what I mean by doing this. A lot of the data we look at could be coming from log files, for instance. So what I mean by log file is that you have a timestamp, and then you have some other fields that might characterize a particular event. So events could be every time a call gets dropped on your LTE network, you record that because obviously that's important. Or every time a customer calls you to complain about the service, that's another type of event that you want to monitor. Because obviously if you have too many calls being dropped or too many customers complaining about the service, then this is bad for your business. So the first thing you want to make sure is that you're actually monitoring the right KPI. So in this case, we're monitoring those events. Could be drop calls, for instance. So you have a point process representing the arrival time of those drop calls, for instance. So you have a timestamp, and when you do a lot of analysis, point processes are great, but they're not so easy to deal with. So the first thing you do is usually you bin your point process to count how many events you have in different intervals. I won't go through the tricky business of actually deciding on what time scale you want to be in your process. You assume that you've done that for now. And so what you have is that as a function of time, you're counting the number of events you've seen. And for now, just ignore everything but the gray curve. But the grain curve. So the grain curve gives you at every hour of the day, over multiple days, how many of such events you see. So this is obviously has clear daily patterns because it has a human activity component in it. And this is over the course of a week. Once you have that grain curve, you're trying to figure out whether any of the points on that grain curve look anomalous or not. If all you have is a grain curve, it's very hard to figure that out. So you will use past information, which I haven't shown you here, to learn the characteristics of your system, and then use that learning to compare that with what you're seeing right now, and decide whether what you see right now makes sense based on what you've learned in the past. So the fundamental part of the exercise is to build a prediction of what value you should be getting right now, conditioned on all the history, on all the historical data. Here, I mentioned that you not only want to know, in statistical terms, you don't just want to know the expected value of your prediction, but ideally, you want to actually predict the whole distribution of your predictions. This is obviously the hard step, but if you can do that, it will make the rest of the exercise a lot easier. So here what I've plotted is that think of it as some kind of expected value that you would be expecting for your signal at this point in time. And the different shades of gray here are different confidence intervals on that estimation. And if you can do that, then all you have to do then is simply compare the grain line and see when it goes outside of your gray bands, and then here you go, you have your anomalies. So all these points here, for instance, you had this ramp up at the start of the day in local time, which meant that you weren't at all expecting those events to happen at this point in time, and you can trigger that as an anomaly. So fundamentally, that's what we're trying to do. We do that at very large scale. If you operate on the 5-minute window, then every 5 minutes, you have to make those predictions across millions of time series, and then take the appropriate action. So here I've talked about this type of scenario here, where obviously you want to predict your distribution of current values based on past values. I might disappoint some of you, but we're not using random forests or things like that. A lot of the stuff you've seen yesterday it's mostly based on statistical signal processing and time series analysis. And we do that either on a single time series at a time, that's the univariate analysis, or to actually extract more value out of the system, we usually use multivariate time series analysis. So I've showed you this type of signal before where, trust me, the same thing happened before with the same weekly periodicity. So it's reasonably easy to infer what value you should be getting at any point in time. On the other hand, when you're monitoring signals that from other types of sensor data, and signals have a lot less structure if you want, it's obviously a lot harder to make an informed decision regarding the direction of that signal. But the principle remains the same, that if you can predict the distribution of future values, then you'll be in good shape. This has been cut off, and it says hard, hard, and hard. So a lot of hard things have to be solved to actually get there. The first one is that obviously you have different types of input signals. So you will probably use different types of algorithms to model your data. But at the end of the day, you still want to be able to unify your anomaly metric, if you want, so that you can rank alarms and severity of alarms between very heterogeneous time series or input KPIs. Another thing that I want to emphasize is that we are building these products and we are selling them. So obviously, we have limited hardware footprint. So you have a certain budget to actually build a solution. You will not necessarily go for something really fancy. You will go for something that works and that fits within your hardware budget. So within those constraints, you obviously want something that will scale and that you can distribute nicely between your computing resources. And finally, probably the hardest thing is to keep your customer happy. Because remember, we have no labels. At the end of the day, the only label you have is whether your customer is happy or not, whether you've done a good job or you've done a bad job with your anomaly detection. So you do a good job when you don't flood the customer with alarms that are useless. You have to remember that depending on how you actually package those alarms to the customer, there might well be someone looking at a screen and having lots of little red things happening every time you send them an alert. So they have limited resources to ingest your alarms. So you want to make sure that you don't send too many alarms. You obviously want to limit the false positives. By that, I mean don't alert when there's actually nothing wrong, because that will also consume some of their resources, some of your consumer resources, and it also means that they do not trust your system. Fundamentally, you're trying to gain your customer trust and making sure that they are ready to act on your alarms. And obviously, you want to rank them by severity in one way or another, so that the customer can then attack the top problem first. So, given those challenges, here are some of the solutions that we use. First, from a data science perspective, and then in terms of engineering. The hardest thing to remember is that you have to build what's called, in statistical terms, a robust system. By that, I mean that when you start doing your anomaly detection, you might look at your past history to train your system, but you don't know whether you had anomalies in the past or not. So you want to be able to train a system that will be robust to the past noise as well. That is probably the trickiest part of the whole system. And obviously, because you don't really control those KPIs, the system might evolve in time, so you want to make sure that you can adapt to changes in the underlying sensor data that you're trying to monitor. I've mentioned it before, I'll mention it again. We have no labels. So internally, what we do is that you do have to build some labels or some kind of unit tests or some test cases that you can say, hey, yes, in this situation, we should not have triggered anything, or in this situation, yes, we should have triggered something. But it's something you have to build, and it's something that comes usually from interacting more directly with your customer to really understand their business case. And here I've said, okay, instead of business case, I'm using the term utility function. What that means is that you want to really be able to quantify the cost of sending them false positives and false negatives. If you can do that, then yes, then you stand a good chance of being able to actually automatically set the right thresholds and do the right transforms on your signals to solve the problem. So what I'm showing here is pretty much the same signal that we had before with periodic, a nice periodicity component. And what we show here, also at the same function of time, is that for every bin, you build a metric that will tell you, that will give you some kind of anomaly indication. And that's really what you work with. So every hour of every day, we can come up with a metric that tells you, yes, every time there's a high value, it means yes, there's a very high chance that this was an anomaly. So what you see here is that those red dots here actually match the spikes that you see in this metric here. From an engineering perspective, I've mentioned the limited hardware footprint. Oh no, I don't have 5 minutes, I have more. And what that means is that you want to be a bit clever regarding the way you use your resources. When you look at, so we use things like intelligent caching and compression on our input data, and we try to use the most appropriate platform to deliver a solution. So in this case, it's an Apache project, open source, called Spark, which we found very good at doing this type of projects. Here's now a quick use case. So this is just a snapshot of one of our applications. So here we're monitoring the drop call rate across different cell sectors of a 4G network. So a 4G network is what you could call a LTE network. So that's what probably most of your phones are connected to right now. Is made of thousands and thousands of base stations. And each base station will be outputting a range of KPIs every 15 minutes or every 5 minutes, or on an event-driven fashion that tells you how they're going and what's happening on that base station. So they'll tell you how many calls they've dropped in the last 5 minutes, for instance. So you can monitor that over time across the entire network and try to detect anomalies. So what you see here as a function of in hourly buckets over a day is that you had it's hard to read here, but that's just different base stations. They're called E-node Bs on the LTE network. And you see here an area where a lot of calls were dropped. So we sent alarms of a critical severity. What this gives you is not only a view of what's happening on each base station individually, but it also gives you a network-wide view of what's going on. And you can then see whether the outage is limited to one base station, or if it's maybe, I don't know, maybe during the night you pushed a new firmware version on some of your towers, and you realize that your scheduled maintenance went completely wrong, and all the base stations where you did a firmware update, they're all dropping more calls than others. So once you isolate the fact that, okay, over that period of time there were issues, then looking at a whole range of other KPIs, you try to do what's called a root cause analysis and understand what is really causing the issue. Going a bit quick here, but in terms of solution, I've mentioned before, we use Spark. So that's a bit of a buzzword now, but what it means under the hood is that you may or may not have heard of Hadoop as a distributed file system. And what you do is that you run Spark on top of Hadoop, usually with some form of cluster resource management, whether it's Yarn or Mesos. And so you ingest a whole range of data streams that you will then fuse and aggregate with other input data that you already have in your system. And then you can do a whole bunch of time series analytics and your anomaly detection. And once you've done this anomaly detection, then you have different ways of interacting with your customer. Either you put that on a user interface, or you have more of a machine-to-machine interface where you actually plug directly back into the customer system. So what happens in practice is that over time, the customer will gain trust in your system, and they give you right access to their trouble ticketing system. So you can automatically raise tickets for them. Last slide. So very quickly again, in terms of conclusion, the lessons we learned in the process. Obviously, I'm giving you a 30,000 view of what's happening here, but the take-home message here is that there is no such thing as one anomaly detection algorithm. There is no silver bullet. It really depends on the type of inputs you want to do anomaly detection on, and each of those different methods will have pros and cons. So obviously, given the constraints I was telling you about, you always try first to have something simple and scalable. I have no use for a super fancy algorithm that takes 15 minutes to run if I get my data every 5 minutes, because I'll be behind from the first 15 minutes and I will never catch up. So a lot of those constraints come into the picture when you have to choose or build the right anomaly detection algorithm. Obviously, you want to adapt to the changes in your underlying data, adapt to the change in your customer needs as well over time. And from an API design, because it is an API conference, we very much favor a black box approach where we try as much as possible to hide the complexity from our developers, so that at the end of the day, from a developer perspective, all you need is your streaming input. It could be a Spark streaming object, or it could be something else. And all you have to do is that, okay, do anomaly detection on this stream of data. Everything else we handle internally within the analytics team, so that we control better the performance of the algorithm, both in terms of accuracy and in terms of hardware and software footprint.